Despite its successes, the Bohr model has a number of problems. Firstly, it really only works for hydrogen and other one-electron systems, such as helium +1 and lithium +2. Keep in mind that in order to use the Bohr model for the other one-electron systems, we have to use a different value of the Rydberg constant, which is specific for each particular ion. Another problem with the Bohr model is that it does not correctly predict the emission spectra for multi-electron systems, which are essentially all the other atoms in the periodic table. So in order to address this shortcoming, we have to develop a new model which is based on wave mechanics or quantum mechanics and was developed by Erwin Schrödinger. Schrödinger introduced the concept of the wave function, which we represent by the Greek symbol psi. And this is a mathematical description of the wave-like behavior of the electron in three-dimensional space. This three-dimensional representation is what we call an atomic orbital and should not be confused with the two-dimensional orbits that we studied in the Bohr model of the atom. These wave functions can be characterized by three specific parameters, n, l, and m, which we call quantum numbers. And we'll learn a little bit more about each of these quantum numbers in the following slides. The first quantum number we will look at in the wave equation is n, also known as the principal quantum number. N must be a whole number, and allowed values for n range from 1, 2, 3, 4, and so on. The principal quantum number describes the distance of the orbital from the nucleus. Below we have figures for three orbitals for n equals 1, n equals 2, and n equals 3. These correspond to the 1s, 2s, and 3s atomic orbitals. As you can see, as n, the principal quantum number, increases, the orbitals get larger, and therefore the electrons become farther from the nucleus. The second quantum number is the angular momentum quantum number, which is represented by the symbol L. Allowed values for L depend on n, and they must be positive integers starting at 0 and going all the way up to n minus 1. So for example, if n equals 1, then L can only be 0. However, if n equals 2, then L can be 0 or 1. And if n equals 3, then L can be 0, 1, or 2. The significance of the angular momentum quantum number is that it describes the shape of the orbital. So for example, L equals 0 is completely spherical, which we call an s orbital. L equals 1 is dumbbell shaped and is given the name p orbital. L equals 2 has 4 lobes, and we call this a d orbital. And L equals 3 is an f orbital. So just to recap, the angular momentum quantum number L describes the shape of the orbital or the type of the orbital. Now you might be wondering where the labels S, P, D, and F came from. Well, the historical reason for those names is that when physicists were looking at the emission spectra that arose from those orbitals, they noticed that some of the orbitals were sharp, which is the name for the s orbital. Some of those emission lines were principal lines, and that's a name they gave to the p orbitals. Some of those lines were diffuse, which is a name they gave to the d orbitals, and then some of the lines were fundamental lines, which is a name given to the f orbitals. The third quantum number is the magnetic quantum number, which is given the symbol m sub l, or ml. Allowed values for ml depend on the value of L, and they must be integers ranging from negative L going through to 0 and then all the way to plus L. So for example, when L equals 0, which is an s orbital, then ml can only equal 0. However, if L equals 1, which is a p orbital, then ml can be negative 1, 0, or plus 1. And finally, if L equals 2, which is a d orbital, then ml can equal negative 2, negative 1, 0, plus 1, and plus 2. The significance of the magnetic quantum number, ml, is that it describes the orientation of the orbital in space. Let's take a look at the magnetic quantum numbers in more detail. We'll start with L equals 0, which is the case for the s orbital. Here's a picture of an s orbital here, and we can see that it is completely spherical. In this case, the orientation doesn't really matter, so there can only be one s orbital. Looking at the magnetic quantum number, when L equals 0, there's only one possible value for ML, and that's ML equals 0. Again suggesting that there can only be one s orbital. Now let's take a look at the case of the magnetic quantum number for when L equals 0, in other words, the p orbitals. When L equals 1, then the magnetic quantum number, ML, can have three possibilities. ML can equal -1, 0, or +1. This corresponds to the three different p orbitals, px, pz, and py, respectively. And here we can see the three different orientations for the three p orbitals. Now it's important to remember the characteristics of the p orbitals and how they differ from the s orbitals. You can see here that each of the p orbitals has a nodal plane. And we can see that in each one of the p orbitals. The nodal plane is a special region where the electron density for the orbital equals 0. Another important feature of the p orbitals is that the lobes for each of the p orbitals have different phases. So as we go from the left side through the nodal plane to the right side, we can see that the phase of the wave changes from blue to red, and vice versa. And this feature is present for each one of the three different p orbitals. At the bottom here, we've put each of the three p orbitals together. Still looking at the p orbitals, you might be asking yourself what the phase of the wave is supposed to represent. Here we've colored them blue and red. Well, on the diagram at the top here, I've drawn a sine wave, as you might remember it from high school. You can see that for a sine wave, part of the wave lies above the x-axis and part of the wave lies below the x-axis. If we color the part of the wave above the x-axis in blue and the part of the wave that is below the x-axis in red, these would represent the two different phases, just like we see for the p orbital. Now these p orbitals are drawn in 3 dimensions. However, for your midterms and final exams, when you're asked to draw the orbitals, you would be expected to draw them only in 2 dimensions. And the diagrams shown below here represent how you would be expected to draw the p orbitals on your midterm or final exam. Here we look at the magnetic quantum number, ML, for the case where L equals 2, in other words, the d orbitals. Now, if you remember, ML must be an integer starting at -L, going to 0, and then going all the way to +L. And so because L equals 2, the allowed values for ML are -2, -1, 0, +1, and +2, respectively. And these correspond to the 5 d orbitals, dx² minus y², dxz, dz², dyz, and dxy. We can see here that the d orbitals each have 2 nodal planes, which are shown right here. At the bottom here, we've plotted all 5 of the d orbitals together to show you what they could look like. Again, on both the midterms and the final exams, you will be expected to be able to draw the d orbitals in 2 dimensions. And at the bottom here, we've shown you how they should be drawn in 2 dimensions. We can see here that the nodal planes, where each d orbital has 2 nodal planes, for 3 of the d orbitals, those nodal planes lie along the axes. For one of the d orbitals, the nodal planes lie between the axes, and that's the case for dx² minus y². dz² is a little bit different, because it doesn't have 2 nodal planes, but it has 2 nodal surfaces, or nodal cones, shown here. So once again, you should be able to draw the d orbitals as well as draw the nodal surfaces or nodal planes. Here we look at the magnetic quantum numbers, or ML, for the case where L equals 3, or the f orbitals. Once again, because ML must be an integer that starts at -L, goes to 0, and then goes all the way to +L, the allowed values for ML are -3, -2, -1, 0, +1, +2, and +3. So we can see that there are 7 f orbitals. Now, you might notice that the f orbitals are somewhat complicated. So the good news for you is that you are not responsible for drawing f orbitals on the midterm or the final exam. However, you should be familiar with them and what they look like. Here, I would like to summarize the concepts we have learned about quantum numbers for the case when n, the principal quantum number, equals 1, 2, or 3. When n equals 1, the angular momentum quantum number, with L, which must be a positive integer starting at 0 and going to n minus 1, must be 0. Also, the magnetic quantum number, ML, which must be an integer starting at negative L, going to 0, and then going all the way to plus L, only has one option, and that's ML equals 0. So we can see when n equals 1, we only have a 1s atomic orbital. When n equals 2, then the angular momentum quantum number L can be either 0 or plus 1. When L equals 0, then ML can only be 0, and this would be the case for the 2s atomic orbital. However, when L equals 1, then ML can be negative 1, 0, or plus 1, which corresponds to the 2px, 2py, and 2pz atomic orbitals. When n equals 3, then the angular momentum quantum number L can be 0, 1, or plus 2. When L equals 0, ML must be 0, and this would correspond to the case of the 3s atomic orbital. When L equals 1, then ML must be negative 1, 0, or plus 1, which would correspond to the case of the 3px, 3pz, and 3py atomic orbitals. When L equals 2, then ML must be negative 2, negative 1, 0, plus 1, or plus 2, which corresponds to the case of the 3d x squared minus y squared, 3d xz, 3d z squared, 3d yz, and 3d xy atomic orbitals, respectively. So you can see that for the case where n equals 1, there's only one orbital that can have the value of n equals 1, and this is the 1s atomic orbital. However, when n equals 2, then we can have 2s and 2p atomic orbitals, giving us 4 possible atomic orbitals for n equals 2. Finally, for the case when n equals 3, then we can have 3s, 3p, and 3d atomic orbitals, giving us 9 atomic orbitals for the case where n equals 3. In part A of this example, we are asked to specify the angular momentum quantum number, L, and the magnetic quantum number, ML, that are allowed for a principal quantum number of n equals 3. And in part B, we are asked to indicate the number of orbitals that are allowed for n equals 3. So the strategy we will use for this case is to use the selection rules for each of the quantum numbers. For the principal quantum number, n, allowed values must be whole numbers starting at 1. For the angular momentum quantum number, L, it must be a positive integer starting at 0 and going all the way to n minus 1. And for the magnetic quantum number, ML, it must be an integer starting at negative L, going all the way to 0, and then finally all the way to plus L. So, if n equals 3, then allowed values for L are 0, 1, and 2, because 2 is n minus 1, or 3 minus 1. Now, if L equals 0, then ML can only be 0, and this would be the 3s atomic orbital. For L equals 1, the allowed values for ML are negative 1, 0, and plus 1, which corresponds to the 3p atomic orbitals, 3px, 3pz, and 3py, respectively. And if L equals 2, then the allowed values for ML are negative 2, negative 1, 0, plus 1, and plus 2, which correspond to the following d orbitals: 3d x squared minus y squared, 3yz, 3d z squared, 3d xz, and 3d xy. This gives us one s orbital, 3 p orbitals, and 5 d orbitals, which gives us a total of 9 atomic orbitals that are possible for the case where n equals 3. In this example, we are asked to indicate the possible sets of quantum numbers for a 3p atomic orbital. Once again, the strategy is to use the selection rules for each one of the quantum numbers. For the principal quantum number n, it must be a whole number starting at 1. For L, the angular momentum quantum number, L must be a positive integer starting at 0 and going all the way to n minus 1. And for the magnetic quantum number, ML, it must be an integer starting at negative L, going to 0, and then going all the way to plus L. So, the 3p atomic orbital. 3 indicates the principal quantum number, n equals 3. P indicates L equals 1. So therefore, allowed values for ML would be negative 1, 0, and plus 1. Where n equals 3, L equals 1, and ML equals negative 1 would correspond to the 3px atomic orbital. N equals 3, L equals 1, ML equals 0 would correspond to the 3pz atomic orbital. And n equals 3, L equals 1, and ML equals plus 1 would correspond to the 3py atomic orbital.